All right, now we're going to talk about something called the ratio test. This theorem 5.16 is a ratio test. So if we have some sort of series of this form, n equals 1 to infinity of an, it's a series with non-zero terms. So if they're all zero, we don't worry about it. But if we have non-zero terms in it, we're going to look at this row. This is RHO. That's the name of that Greek letter. So we're looking at rho, and it's going to equal the limit of a of the n plus 1 over an. It's the absolute value of the whole thing. So we take that limit, and then if we have a row that's greater than or equal to 0 but strictly less than 1, then this converges absolutely. If our row is big, however, greater than 1, or if we just determine that the limit is infinite, which infinity would certainly be greater than 1, then we diverge. And strangely enough, if number 3, if we get exactly 1, does not provide any information. So if you get a row equals 1, you just say the ratio test is inconclusive. Now that means you may have to use a different test as well, but the specific questions we have here, it states that use the ratio test to determine whether our series converges, where an is given in the following problems. State if the ratio test is inconclusive. So it's telling us to use the ratio test, and one of the caveats is that we have to determine, or we have to let them know that it's inconclusive if we get the row equal to 1. So let's do 317. We already know what the answer to this is because we've done it a couple different times, but we're not going to use a comparison test this time. Now we're going to use the ratio test. So we're going to take the limit, or rho, that's sigma, rho equals limit as n approaches infinity of the absolute value of 1 over n plus 1 quantity factorial over 1 over n factorial. Well, that equals the limit of 1 over n plus 1 quantity factorial times n factorial over 1, because we're dividing by so we're multiplying by a reciprocal. Well, n factorial is, again, just n times n minus 1 times n minus 2, and n plus 1 is all that plus n plus 1. So this just equals limit, and that's as n approaches infinity, of 1 over n plus 1. Well, we know that this is 0. And certainly 0 is strictly less than 1. Therefore, the series converges. And even specifically, it converges absolutely. We can even write that. I don't think the question asks us for that, but we're giving it to them. All right, so let's try this 319. All right, if we use the ratio test, we get rho equals n plus 1 quantity squared over 2 to the n plus 1. And I'm going to start, since we're dividing by we'll divide, that's fine. N squared over 2 to the n. Well, this equals n plus 1 quantity squared over 2 to the n plus 1 times 2 to the n over n squared. Well, the 2 to the n over 2 to the n plus 1 is just 1/2. So this is going to be 1/2 times n plus 1 squared over n squared. And if we want, we can convert that all into one thing. But I'm going to take a look at that. And that's our rho. And actually, we need the limit of all of this. So let's do that. from this one too. Can't lose this yet. We haven't taken the limit. All right. So we know that the ends are going to be positive, so we don't have any negative values here. We can lose the absolute values, and that will be just fine as well. So we're also going to use L'Hopital's rule. So this equals limit as n approaches infinity. I'm going to, again, drop the absolute values. It doesn't matter here. So the derivative of the top is going to be 2 times the quantity n plus 1. The derivative of the bottom, we've got 2 times n squared. That gives us 4n. Okay. We can now use L'Hopital again. So that equals limit as n approaches infinity. This one is just 2 over 4, which equals 1/2. So the limit of that is 1/2. Now, please note that 1/2 is strictly less than 1, which implies the series converges. Absolutely.